slide. All right. Here we've got it. And we'll even turn on the bulb. And this time I'll mark you present. Okay. I got you last time too. Okay. Trey is here. Actually, my linear. Okay. You've heard the announcements. They're the same ones as before.
Yeah.
Did you get the topic?
Yeah.
Okay. Now, that reminds me. I need to take this out. Sorry.
You might want to make a quick run to the store real quick. No.
Okay, sure, no problem. I may get started talking, but you. Yeah. All right. Well, Treddy had to step out, so I'll give you the announcements. This isn't extraordinarily important, probably, but because y'all don't seem to be on campus today, and this won't be loaded by the time it's over with anyway. But normally, my office hours today on Wednesday and Monday. Wednesday are 3:15 to 5:15. However, Monday when I drove in, my car almost shut down on me. It did shut down, but I was able to get it started back. Went into campus, left it parked here. Finally got it to a place yesterday. They didn't have the parts, so they kept it overnight. So they just called this afternoon, when I was eating lunch, and said that the head was, they thought it was just a hose on the radio. What happened, the hose sprung a leak on the radiator system and it didn't give me any indicator lights that I was in problem. And I drove to campus with basically hardly any fluid, but it still was running. And I didn't know it because it still didn't indicate it was hot. And so what has happened, the head got warped or something, I guess. And now they say when they replaced the hoses, that was the original problem. And when they put coolant in the system, it started coming out the spark plugs. That's not good. So evidently my head is leaking. I don't know if it's just a blown gasket. I don't know. I talked with them over the phone, and the woman who was doing the tour, I don't think she really knew what was going on. She said the car was not drivable. I drove it over there. I don't see what they did could have made it undrivable, but anyway. For my office hours today from 3:15 to 5:15, I'm going to have to be dealing with that, and I will not be in the office the entire time. I'll probably have to go get the vehicle or arrange to have it towed or something. So it's kind of a mess right now. So I don't know. I'll be in the office part of the time because I'll be on the phone, but the other part of the time I may be out of the office. Okay, there's that. Friday coming up, there is a presentation at 10 o'clock in the morning on the Birmingham East Campus in the A.G. Gaston Auditorium by I think it's UAB Theater production of Shakespeare's Taming of the Shrew. Now, that was a comedy by Shakespeare, which probably was one of the most famous comedies he had. A major motion picture was made of it back in probably the 60s or 70s. And it's a very well-known play. Well, UAB, of course, people don't like to do the same thing over and over again, so they change things around. The story, original Shakespearean story, was a very strong-willed, opinionated woman, and the man was trying to tame her, taming of the shrew. And the comedy is all their interactions there. UAB has decided, or whoever redid the play, decided to make the man the very difficult person, opinionated and all like this, and having the woman trying to tame him. So anyway, that's going to be Friday, 10 o'clock, Birmingham East Campus, A.G. Gaston Auditorium. All right. Now, we last time were in, let's get on to differential equations. We were in chapter 2, just about to wrap up chapter 2, and this is first order differential equations. 2.6 is a numerical method, and we talked about the Euler method. Okay? By the way, Euler would be a good paper topic, or how did he develop this method, other things. Here's the caveat on page 79. We almost finished, but we didn't get that. Euler's method is just one of many different ways in which a solution of a differential equation can be approximated. Although attractive for its simplicity, Euler's method is seldom used in serious calculations. We just did all those calculations. Guess what? They weren't serious, okay? It was introduced here to simply to give you a first taste in numerical methods. We'll go on to greater detail in discussing numerical methods that will give you significantly greater accuracy, notably the fourth order Runge-Kutta method, referred to as RK4. So there's two more potential paper topics. Who was Runge? Who was Kutta? Okay? And what's more, what were the first, second, third order Runge-Kutta methods? Or, how did they develop, especially RK4 or any of the early ones? Okay. So that just was to give you other possibilities. Now, numerical solvers, regardless of whether we can actually find an explicit or an implicit solution, if a solution of differential equation exists, it represents a smooth curve in the Cartesian plane. Smooth curve, okay? The basic idea between any numerical method for first order or ordinary differential equations is to somehow approximate the values of y of a solution for pre-selected values of x. Okay? Let's go on down. A computer program written to either implement a numerical method or render a visual representation of an approximate solution curve fitting the numerical data produced by any of these methods is referred to as a numerical solver. Okay? If you got a computer program that is going to approximate or estimate answers, that's a numerical solver. And with that, some software packages simply plot the generated numerical approximations, whereas others generate hard numerical data as well as the corresponding approximate or numerical solution curves. Now, see, you don't have a book, so for right now, I'm going to just show you what they're talking about. Okay? Here is an exact solution. It doesn't say what your equation is, differential equation is, but the blue curve you see there is your exact solution at any time, at any value t on x value. Okay? They give you that at x equals 0, y is equal 1. Okay? Now, Euler's method does along like this at some things. So it underestimates throughout. Pretty good for a short distance, but gets worse and worse as you go. The RK4, that's Runge-Kutta 4, it is exact at 1, 2, 3, 4 places, the original plus 4, and it fits pretty nicely in between those 4. Now that's covered later in the chat book that we probably won't get to, but you can always go over there and look at it if you're interested. Now,
what page is that? I got it.
that's page 80. Oh, you got your book. Okay, page 80. And then using the numerical solver, they just show one that gives you a really lousy curve. Okay, the figure 2.6.4, a not very helpful numerical solution curve. So not all of these will always give you, even though we're using these for generally for differential equations we can't solve analytically, we get these numerically. Sometimes the numerical solutions are not very good either. Okay, and that's what that shows. So homework exercises here, if I didn't assign them before, do number 1, do number 3, do any of the odds 5 through 9, do number 11. Okay, and the rest of those you can look at if you like. Now that finishes chapter 2. Did I give you your test on chapter 2? Okay, I'll do that next. But if you do want to look at a few more, there's a chapter 2 review. Any of the odds 1 through 10 would be good to look at. 1 through 11, 13, 15 or 17 or both, and any of the odds 19 through 25. Either 27 or 29 or both. Do 31, try it. 34 or 33, try it. And 35, any of the odds 35 to 39. Okay? Now, I'm pretty sure I got that test run off, but I can't remember for sure. This week has been a haze because of all the mess I've had to do with the car. I haven't gotten Victor's test back yet, so I can't give you your first test back, but you did quite well on that. So let me see if I can find the second one. Like I said, I'm pretty sure I had it run off. I have a whole bunch of these done Monday. There it is. It's back. There's your second test. So let me get these. Back where they belong, they separated. All right. And while I'm doing this, sorry to take up fast time. I needed to get these for label on help. When I'm looking for them, I won't be able to find them. That I think. Nope. Okay. Sorry to take less time to do that. Notice they were out of place earlier. All right, let's move on. Okay, chapter 3 is modeling first-order differential equations. There's nothing in the course description that said anything about the modeling. It's some really good stuff, especially if you may deal with things like growth and decay, bacterial growth, nuclear stuff, decay, half-lives, those kinds of things. Carbon dating, if that's of interest to you, there's a blurb in here about that, and about the chemist Willard Libby, who came up with that.
Oh, that's not where my research paper now.
What's that?
William.
Willard, huh? Willard Libby?
Yeah.
Have you turned that in? Nothing.
Oh,
You
my
haven't.
laptop right now. I got it. Maybe
Right.
on.
Okay. Age of fossils. I mean, all this is really interesting stuff. Ernest Rutherford is mentioned, radiometric dating, potassium argon method of dating. There's just all sorts of ways to go about doing this. Newton's law of cooling and warming. We talked about some of these early on. These are all models that they have to do these. Cooling of a cake or something else like that. Mixture of salt solutions where you got input and output. Your circuitry, LR, LRC, RC circuitry, you can model with this. So it's all modeling, and it's all interesting. We just don't have time to do all that, but if that's of interest to you, there's nonlinear models that you might want to look at. That's in 3.2. Logistic regression, logistic growth. My wife uses that a lot in disease studies and growth studies, population studies, those kind of things. Second order chemical reactions, nonlinear. That's all in 3.2. 3.3 is modeling systems with first order differential equations. Radioactive series again. Mixtures again. Lotka-Volterra model, predictor prey models. There's all sorts of things you can use here. Kirchhoff's first law, second law. I think we've hit several of those before, so we're not going back over them again. Okay? Now, chapter 4 deals with higher order differential equations. That we are going to do. Okay? And this is a very long chapter. It's probably going to wind up taking a lot of the rest of the term, okay, because it's got 10 sections in it. We probably won't do all 10, but we're going to do several of them. So let's look. We'll do first preliminary theory, linear equations, okay? But this is going to be higher order differential equations. Now, a little bit of review. A general solution is a family of solutions defined on some interval I, contains all the solutions of the differential equation that are defined on that interval I. Only in the case of linear first order differential equations were we able to obtain general solutions by paying close attention to certain continuity conditions imposed on the coefficients of the equation. Because of our primary goal in this chapter is to find general solutions of a linear higher order differential equation, we first need to examine some of the basic theory of linear equations. So let's go back. It's going to be partially a review, but then introducing some new stuff. Initial value problems, and there's another kind called boundary value problems. Okay? And when we're dealing with an nth order initial value problem, not just linear, but initial nth order, this is going to start off really complicated looking, but the concepts are pretty simple. But here's how they do. For instance, this is what you're asked to solve. Let me get my pen set up. Okay. A sub n of x, d to the nth of y, dx to the nth, plus a n sub n minus 1 of x, d to the n minus 1 of y over dx to the n minus 1, plus, and it keeps on doing like that, dot, 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 until finally you get down to a sub 1 of x dy dx plus a sub 0 of x times y. And that's equal to some g of x. All right. Looks pretty messy, doesn't it? So what we have here is an nth order. That means you're taking not just the first derivative, second, third, it could be any of those, fourth, fifth, nth order differential equation. You're taking up to the nth derivative. That shows up in your problem, okay? Now, there are coefficients for that. The coefficients can be functions of x. You know, if you think of a polynomial function, that's what this sort of looks like. A sub n, x sub n plus a sub n minus 1, x sub n minus 1. So it's that sort of looks like this. Well, this is a differential equation where your variable, say, is your nth order derivative. Your coefficient for that is not just a constant, but can be a function of x. Notice what it can't be. It can't be a function of y. Because if y was in the coefficient, that would not be a linear function, a linear differential equation. Because you would have y's here and derivatives of y in the same term. All you have are derivatives of y, and notice these derivatives of y are not squared or cubed or anything else. These are second, third, and fourth derivatives, not powers, derivatives, okay? Now, all your coefficients may or may not be functions of x, down to your last one, which is the zeroth derivative of y, which is just the function y, okay? Remember, y is also a function of x. We haven't written that in there, but it is. And over here on the right-hand side is only functions of x, okay? You can't have y showing up over there either, okay? So the only place you have your y's are the y's and the derivatives of y. X's can show up in the coefficients, and they can show up in the function on the other end, but y can't show up in any of those functions, okay? Y's only show up as those derivatives. Okay. Now, that's your differential equation part. Here is your initial value part. Subject to, you're asked to solve that, subject to y of x0 is equal to y0, y prime of x0 is equal to x, y1, down to y sub n minus 1, y, the nth minus first derivative of y evaluated at that same value x0 is equal to y to the n minus 1, sub n minus 1, okay? Now, what does that mean? Now, here's my little aggravation, you might say, with this. X of 0 doesn't have to be the first value. This could be 7. It doesn't have to be 0. It doesn't have to be 1. It could be some value in the middle somewhere, okay? But you're doing the function of that value is derivative of that value, is the next derivative of this value is nth minus first derivative of that value. You're doing all those at that same point. So they call that point the initial value. So this is called an IDP, initial value problem. Okay. Later we'll get into boundary value problems which may occur at more than one axis. Okay? In other words, the boundaries. You have the boundary here and the boundary here, and you know the information at both ends, not just at one end, okay, or at one place, okay. So, the next thing they talk about is a concept of existence and uniqueness. Okay? And that's theorem 4.1.1. You've got your book. I don't know that, pretty sure one of them has, but maybe not both of them have the book. So just for now, I'll go on and write this in. Okay? So I'm going to erase that ink so I can write this in. This is theorem 4.1.1, existence of a unique solution. So this existence and uniqueness in the same thing. Now, we want our let the a sub n of x, that was that coefficient function of your nth derivative, your a sub n minus 1 at any value x, and all the way down to a sub, yuck, I said sub and put a parenthesis, duh. A sub 1 of x and even a sub 0 of x, okay? And g of x, all these functions of x. Let all these functions of x be continuous, okay, on the interval I, some interval I, and here's a requirement, it looks familiar, I hope, a sub n minus 1, no, a sub n not equal to 0. For every x on the interval. In that interval I. Okay. That's the given. Oh, that's part of the given. Okay? Here's the next part. If x equal x0, some specific value is any point on the interval, okay? Then a solution y of x of the initial value problem exists on the interval and is unique. Okay? Then the solution y as a function of x of the IVP exists on the interval and is unique. My writing's getting worse. Okay? All right, now what does that say? Okay, remember that big, long, hairy description of what your higher order differential equation was. Linear. Okay? Now remember the coefficient functions for each of those derivatives, higher order derivatives you had, the a sub n of x, a sub n minus 1, all of those functions of x down to the function that went with the first derivative and the function that went with y itself. Okay? And what was on the right-hand side, all those functions of x be continuous. That's a requirement on that interval that you're dealing with. And that first one, a sub n, cannot be the 0 function. And here's why. The only reason that's true, we've already specified this is an nth order partial differential equation. Well, if a sub n is 0, then the nth order doesn't exist. Well, it may exist, but that term is 0, okay? So then you'd have an n minus first order differential equation. So for that to be an nth order differential equation, a sub n can't be 0. Any of the others can, but a sub n can't, okay? It could be positive, negative, large, small, anything, but it just can't be 0. For every x on the interval I. Now, so that's needs to be continuous if a sub n not equal to 0 for all x's in that interval. Now, if x is equal to x0, if that value is on that interval I, then you can conclude that the solution for y sub x of the initial value problem does exist and is unique. Okay? You can assume that. If those are all continuous, then that sort of guarantees that your solution exists and is a unique solution. So let's look at example 1. Here's an initial value problem. I think they're going back to this thing that I really don't like. 3y triple prime plus 5y double prime minus y prime plus 7y is equal to 0. Okay, that is your differential equation. Third order, ordinary, linear differential equation. Okay? Now, notice here, your a's are all constants. They're not functions of x, they're just constants, which are functions of x. X doesn't show up anywhere. Okay? Here are your initial values, and they've chosen the value x equal 1 to be your initial position. So y of 1 is equal to 0. Y prime of 1 is equal to 0. And y double prime of 1 is equal to 0. Okay. So those are your three initial conditions. Initial, not because they started there, but because whatever value you're doing one for, you're doing for all of them there. Okay? Now, just looking at this, you see if you let y equal 0, which you call the trivial solution, if y is equal to 0, then 7y is equal to 0. The first derivative of y would be 0. The second derivative of y would be 0. The third derivative of y would be 0. So every term is 0, and that's the solution, the trivial solution. But guess what? All these are continuous functions, and this one's not 0. So guess what? You found the trivial solution. You found the unique unique solution. There's only one, what do they call it? That solution exists and is unique. We found it, that's the only one you got. You're not going to find any others. Ever, okay? Follow that first theorem, okay? Because the third order equation is linear with constant coefficients, it follows that all the conditions of theorem 4.1.1 are fulfilled. Hence, y is equal to 0 is the only solution on the interval that contains x equal 1. Okay? There aren't any others. Okay, let's go to example 2. That was almost too trivial, wasn't it? Huh? Yeah. Okay. So let's go to example 2. You should verify that the function y. Now here is what they do, and it sort of gripes me. Y is equal to 3e to the 2x plus e to the minus x, no, minus 2x, minus 3x is a solution of the initial value problem Here's the initial value problem. Y double prime minus 4y is equal to 12x. Okay. Okay. I lost the function there for a minute. That's your differential equation. Here's your initial, oh, by the way. Oh, I've already erased them all. Sorry. Oh. You go back, you got your book. Go back to 4.1.1 on page 119 when it says solve. Notice you have the function and n derivatives of the function. Okay? So it's an nth order partial differential equation. Ordinary differential equation. Notice how many initial conditions you have. Y prime, y double prime, y triple prime, up to y to the n minus 1 prime. But you see, y itself was not prime, so you actually have n initial conditions. That example 1, a third order ordinary differential equation, y triple prime, and then they gave you 3 initial conditions, y prime, and y double prime. Okay? So basically, I hope what you're sort of getting to see is that for every degree in your polynomial, degree in your differential equation, you need to have at least one initial condition that corresponds to that, okay? So that's what they're saying here. Y prime minus 4y plus 12x is equal to 12x. And guess how many conditions you have? Second order ordinary differential equation, linear. You're going to have 2 initial conditions. And they've got to be y of 4 no, y of 0 is equal to 4. I got lost there. Yeah. That's y. I said it again. Y of 0 is equal to 4. Keep wanting to write y of 4 is equal to 0. Not. Y of 0 is equal to 4. And y prime of 0 is equal to 1. All right. I'm losing my voice again, and I was just looking. I've got another 30 minutes of class. I don't know if I can talk for 30 minutes without getting something to drink. Let's finish this problem, and if it's no better, I'm going to pause for a minute and run get a swig of something because I'm dry. Okay. All right. Now notice again, second order differential equation, two initial values. Okay. You have to have a match like that. Number 1, this is a linear second order differential equation. Linear because there's no function of y here, or there. Okay. Y is here, but that's from the derivative of the function. There's no other function of y multiplied by that. Your a sub 2 and a sub 1 have no connection with anyone, you know. There is no y in any of these functions. Coefficient functions are over here. And oh yeah, and there's no cross products either. You don't have, or powers. You don't have this squared or this times a y prime. You can't have any of those for it to be a linear function. Linear ordinary differential equation. So this is a linear ordinary differential equation with second order and with two initial values given. Okay? Your constants are continuous, 1 and -4. Your function on the right-hand side, 12x, is continuous. It's a linear function. That's no problem. So everything fits. There should be one and one only unique solution. They're saying verify that that is a solution. Well, how do we go about doing that? It's what we did back in chapter 1, remember? In order to verify this satisfies that, we've got to take derivative. So y prime of this function they gave us would be what? Yeah, derivative of the first. Okay, we're doing y prime. Here's your function y. We're doing y prime of that function.
Oh, okay. All right.
6 e to the 2x.
Plus?
X will come out minus because that's the minus 2.
Oh, yeah.
Yeah.
Oh, minus
2 e to the minus 2x.
minus 3.
Okay. All right. So that's your first derivative of that function. We don't really need it in the problem because it doesn't show up as itself, but we need it before we can do the second derivative. So what's the second derivative? 12e to the 2x.
Plus 4e raised to the negative 3.
Okay.
0.
And then plus 0. Okay. Now, what they told us that I'm not going to make it. I hope I will. Okay, so let's write down what y double prime is. 12e to the 2x plus 4e to the minus 2x. Okay? Minus 4 times y. And there's your y. So let's do a minus 4 times it. Yuck. Okay. I just can't believe it. Okay. It's minus 4 times y. So that'd be a minus 12, right? Let's just do, just meant to do my eraser. Now I went back to my pen. Okay. We're doing a minus 4 times that. So that would be a minus 12 e to the 2x minus 4 e to the 3x okay, minus 12x. Okay, I also want to make sure I haven't skipped any terms. Nope, plus 12x.
Yeah.
I knew that. That's what I knew there was a sign change there. So this is minus 4 times the top would be a minus 12 4 plus 12x. Okay? Now, that is supposed to be, and this is what we're trying to verify, this is supposed to be equal to 12x. Well, let's see. There's a 12e to the 2x and a minus 12e to the 2x. A plus 4e to the minus 2x, a minus 4. Ooh! That's a minus 2x. I don't know how I got a 3x, positive 3x in it, but there's a minus 2x. Those go away, and 12x equals 12x. Yes, we verified it. Okay? Or not maybe all of it. Okay? Because you also have to verify the initial condition. So let's plug in y is equal to 0. So y of 0 is equal to 3 e to the e to the, what's e to the 0? 1. So that'll just be 3 plus 1 minus 3. Oh, no. Sorry. Of 0. 3 times 0. Okay. And what's 3 plus 1? 4. That condition's met. Now here we do need the y prime. It wasn't just as a stepping stone, but here we go. Y prime of 0. Oh, my throat. Is 6. Right?
Oh yeah, I was looking at the wrong equation.
Right.
Yeah.
6
Minus negative
2 minus 3. And that is 1. There it is. Y prime is 1. So we verified that the differential equation that equation satisfies the differential equation. That equation satisfies the first initial condition and the second initial condition. But we had to get our derivatives here. So that's what we were doing, verifying. Now, so that given function is the unique solution on that interval I. Now, what interval I is that? Any interval that contains, goodness gracious, my mouth is so dry, that contains 0. Okay, x equals 0. Any interval containing that. Okay. All right, I think there's another one here to verify. But before we do that one, let me run and get something to drink. I am sorry to do this, but I don't think I can talk